Record. Yeah, I think I'm recording, and I need to hide the controls. So, good morning, Monday again. Exciting. So only 2 weeks until Christmas. You don't look excited today. Monday, I see. Wow. All right. Yeah, what is on the menu today? So today is actually my last class in this course, and so as you correctly noticed, so there is a class scheduled for tomorrow, which unfortunately will be cancelled because it was meant to be a guest lecture, and the person who will give it, who's supposed to give this class, is on sick leave. So I will cancel tomorrow's class, so there will be no lecture in this course. However, next week you're supposed to monitor the schedule. So I promised you another guest lecture about SAT solvers, satisfiability solvers, applied to the formal verification of software or code. So this class was promised to be given by Per Lindgren, a prof at our department. I will come back with the exact time, so you will see it in the schedule. So 2 messages: no lecture tomorrow, and there will be 1 class before Christmas. Yes, and then basically you do the remaining labs, assignments. I grade this course, and we will live happily ever after. Yes, so exciting it is. Right, but today is, as I told you, the last class, which somehow will summarize the content of the second module in this course about knowledge representation. And so we used a specific language for this, started from RDF, and then we eventually converged to OL language with all the supporting tools for querying and such. Why do we need OL? I mean, in which context are we studying this stuff? Again, I asked the same question, pretty much same question last Monday. Yeah. So OL, why? In what context? Why is it worth sitting here today? Except for, of course, seeing me. I'm also glad to see you. No, seriously. Knowledge description, absolutely, yes. Knowledge description. It's a kind of specific knowledge description, so it meant to be a super huge thing, annotating the web. But as I commented several times, so it has its own application, well beyond semantic web technology. And semantic web, the idea is really interesting and challenging if you think about it. So you want to convert digital resources into knowledge, and you want to query, well, at the end you want to enable semantic queries. So you want to not only do keyword-based search, but really search for concepts. So you want to implement some reasoning. But again, ontologies, well, the term ontologies, and ontologies is a technology, it exists well outside the concept of semantic web. So it's a generic way to represent knowledge. And in this case, OOL is one of the languages that can be used to construct ontologies and also implement reasoning. So today we will be talking about well, OOL reasoning and some logic, some theory behind reasoning with OOL, so that it's really kind of come in the context even of the first module. So where we studied propositional logic, first order logic, and such. Again, okay, so you had a brief look in the next slide. Why would we need ontologies practically? I mean, we as engineers. Why? Yes.
Otherwise, we can't do lab 2.
Huh?
Otherwise, we can't do lab 2.
Yeah. And of course, you will fail this course. Absolutely, yes. But more than that, I mean, is there any use in ontologies? Why, in principle, we would like semantic description of certain domain of technology or
like structure information or knowledge.
Can we live without ontologies and principles? Now, I'm talking about purely from the developing of a system, of a technical system. So you want to develop a technical system to solve a problem, some world problem, or problem from a real world. Can you approach solving it without ontologies? Yes, you can. I mean, if problem is sufficiently simple, you can kind of apply some common sense and common sense approach and solve it. However, so the more complex technology becomes, the more knowledge is kind of in-baked in it, and then it's very hard to kind of keep everything in a very structured manner inside a head. So you need some tools to actually even assist in developing or solving one or another real world problem. So again, so on the level of definition, so we can any problem can be dissected into a kind of more scientific part, so understanding the nature of the problem, so the relationship between different concepts, etc., and engineering. So basically, you want to take parts of this knowledge, combine it into a certain way, and in a certain consistent way, so that not contradictory way, and get a solution. And again, so now I'm doing kind of hand waving, but do you see a point with these two bullet points? I mean, try to kind of reflect it on any problem you want to attempt to solve. Like you want to develop a software for something, an algorithm. So the coding itself and the development of the algorithm is the engineering part. But before you're doing that, so you implicitly or explicitly, you think about the domain that you for which you create this piece of software. Hopefully, you understand the relationship, and then you incorporate this knowledge into your product. And as I said, so some questions or in some problems, probably it's enough to have more or less unstructured documentation. So, for example, description of a process. If you work as a web developer, for example, you want to develop a system, I don't know, for Försäkringskassan or whatever. So they describe, so what do they need to do, some kind of in more or less structured way, and then you attempt to deliver this functionality. But what if, for example, you want to combine proteins to see whether they are compatible, so to invent a new drug or something? How many proteins are over there? How many? I mean, what are the relationship between all these proteins? So again, I'm not an expert in proteins, that's for sure. But at least from my level of understanding, I can tell that it's quite complex business. I mean, you need to be really, really involved in this area in order to understand which protein comes along with which. The same goes for I mean, in the same medical domain. So any take any disease, so the diagnosis of a disease, so any parts of the body. So it's I mean, it's a very, very complicated knowledge. So it is possessed by experts, the doctors, the specialist doctors, and it takes years to get trained on that. And yet, and training a doctor is part of the this engineering stuff. And even doctors, they need some kind of reference base to see, I mean, how to approach solving one or another disease case. So basically, we need to speed up the development. We need a kind of support if we really talk about complex domains. And it is here where we would need some structured representation of the knowledge with relationships and different properties and properties of different types, etc., etc. Again, so I think you asked about some specific examples. So connected to OL. So, for example, SNOMED. So it's one of the is the largest medical ontology. So if you go to SNOMED.org, so you can find lots of information about how to use it. So so there is so basically you can download this ontology, open it in Protégé, and well, start using it, querying, making your own rules. We will be talking about rules, and this is also part of reasoning. So reasoning is not only I mean, in the context of artificial intelligence, we think about kind of automated reasoning, so that a computer system wants or will produce a new knowledge, but from the practical, from the applied perspective. So, I mean, reasoning is also about for example, constructing new rules. So if this, then that. So we will be talking about rule-based reasoning today. So talking about genes, so this is yet another ontology. Go, geneontology.org. So with a comprehensive description of all the genes and stuff. And so just before the class, so let me see. I downloaded this genes ontology. So if you Google like genes ontology OL, so it will give you one of the first hits. And so you again, so this is your lab 2 more or less, pizzas, but now genes. So people took care of structuring so this domain of knowledge, so that you can use this machinery of constructing queries, constructing rules, new rules, and contributing to development of whatever concerning genes. Right. So this is talking about practical applicability of what we are studying. So OL language. So this is a language. It's ontology description language. It was created by the web community, but its application goes well beyond the original semantic web, and it can be used practically in other scenarios as well. So let me go back. I hope they will not collapse into here, as it was with the library a couple of years ago. So we will come back to these two examples from the point of view of a specific type of logic that is implemented by OL, which I will tell about today. So the original idea with OL, and remember, so now maybe it's a good time again to do this recap. So the flow of arguments. So the whole thing started with what? RDF. What is RDF? Description framework. What is it good for? Just annotating resources. Just, I mean, XML format for annotating basic concepts in the web context, of course. But then, so what was the next step again? So after RDF, we talked about RDFS. So we needed an extra support to represent more complex concepts like classes, subclasses, properties, organize properties into classes of properties, etc. So, so that at the end, when we describe a resource and a relationship between resources, we can kind of reference this hierarchical description. And then, RDFS is good for creating this simple, more or less simple ontologies. But the world is more complex, obviously, and we needed extra support for different types of properties, like inverse property, transitive property, so that if property applies to one, so it's kind of propagated to another concept, and other things. I will not list them. So, and basically, maybe you don't need to be stressed about remembering. So all these aspects. But again, the reason behind creating OL was to make it expressive enough to describe complex relations between data, between concepts, between knowledge. And at the end, so it was OL was created, and it has a sound logical basis, so it comes along with automated reasoning. So we will be talking about what kind of reasoning it supports, and also about reasoners. So the algorithms underneath the reasoning. So about reasoning. So these are the instances of reasoning that OL supports. So here is notation. So knowledge base, some concepts. R is a relation between concepts, say son of, or so if we talk about somebody eating something, so eats, is a relation between the subject and the object what it eats. And individuals. So this it will come kind of in a repetitive manner. So we have concepts, and then we have individuals in the ontology. And even I don't know if I have it on the next slide. No. So there's T boxes and A boxes. So the terminology boxes, terminologies and assertions. So there's some specific individuals of given terms. So what you can do, you can see whether your knowledge base entails certain assertions. So subsumption checking. So whether one concept is a subclass of another concept. Well, equivalence checking, consistency. Satisfiability. So if you give a logical expression, we will have an example later on. Does your knowledge base support this logical expression? So is this an expression that you write contradicts to the facts that are presented in the ontology? So this is about concept satisfiability. Consistency is well, basically checking the ontology itself, whether there are contradictory facts. So here, this weird character here, it's actually two characters. So it's not entail, not entails. So and that what is happening. So when you work with Protégé, for example, so when you construct an ontology, so sometimes it can it starts to complain that so certain subclass doesn't so it constantly checks the consistency, so that some properties are contradictory, for example, or property for individuals are contradictory and such. So this is also a reasoning that happens behind the scene. So on consistency of knowledge base. So in this case, again, so maybe I hope it's not confusing. It is sometimes for her, it could be confusing, I guess. But reasoning can be of different types, like automated reasoning, so processes happening on the background for checking something, but then also more engineering-based reasoning. So that's what you can do with ontologies. And so if you have an ontology, so you can create rules. And again, why would you need to create rules? Maybe you came up with some, I'm maybe fantasizing or speculating here. So if you came up with some new relationship between proteins in certain combination, so you can you can create a rule. So if this protein goes along with this one, then it belongs to certain class. So you create this rule, but I mean, by this you also create a new information that is not originally present in your initial ontology. And in logic, in logic programming, so this type of rules are known as Horn clauses. Again, a smart term, but the only thing it means that it's a kind of implies or if-then rule. So as simple as that. So if certain concepts or facts hold, then it implies something else. And then you so depending on the application area, so you can construct some diagnosis rules, legal reasoning, business rules, etc., of this kind. And again, so in the context of OL, or rather in the context of semantic web, so it meant so the ambition was big, so to say. So first of all, the whole ambition with semantic web to kind of convert web of data into web of knowledge is ambitious, but also the ambition was to share this knowledge and to share new knowledge. And as part of this semantic web standardization, there was a development of markup language for rules of this kind. So to work with ontology. So if you come up with a new rule and then applied to a certain ontology, probably you want to publish it, because this rule kind of extends this current knowledge. And as such, so this initiative was to created to design this rule markup language. And so in this working group, the focus was on really to make it interoperable with industry standards. And today, connected to OL, we will take a glimpse, really like high level insight into a variant of this rule markup language, which is called SWRL, so SWRL, Semantic Web Rule Language. So it was created kind of on the side of OL language, and again, so the idea was to so with this language you would write this kind of constructs, horn clauses. And the rules will be expressed in terms of concept described in OL. So classes, properties, individuals. So what we will see now, so we, well, I will go through some slides, so overviewing the basics of language, but given an ontology, so I will actually complete this example of downloading an ontology from Wikipedia, and then so based on this ontology, we will create a new subclass which didn't exist before, just by creating a rule and letting reasoner checking the consistency of this rule against the database and populate this new class with according to the desired conditions. Yeah, so the rules will have two parts. So and again, on the level of terminology, antecedent and consequent parts you can define, and so basically the body and the head of the rule. And so there will be an expression, a logical expression in the first part, and some concept in the head, or maybe a complex. So here is an example. So these atoms will be all classes or all concepts terms and relationships between them. so in this format, and then we'll so based on this rule, so we will derive so we will analyze the ontology, and we will populate a new property, for example, in this case, but it can be a new concept, for example. I don't want again to spend time on going into details or vocalizing all this syntax details, and rather so you can find, if you happen to work with this, so you can find all the documentation here, so in on the web. Maybe in our context, you can also try it in your lab too. So I put it as an optional part. So, but if you want to try it, so you then probably you will need to go through some examples from the web. But what we need in this, I mean, for the example I want to show, are some concepts or logical operators, operations that allow to analyze existing facts in the ontology. So in this very straightforward manner. So you see some algebraic operations, comparison operations, and such. So let us do this exercise so that I couldn't complete last time. So we will go to a Sparkle. So you remember Sparkle is a query language for ontologies. So we go to dbpedia.org. Sparkle. Yes. Yeah, so this is the search motor for the large ontology of dbpedia. So here is the server name, the URL to the server, where all the concepts are defined. So we need to remove this. Let me see. So what do we want here? So let me copy it first, and then I will make it nicer somewhat. So here we define prefixes for different namings. Just here we have N3 statements or conditions. No conditions, sorry. So this is a construct statement of Sparkle. It means that we want to construct, we want to create well, RDF description in certain format, and this is the N3 notation for this description. So what do we say? What do we see here? So we define person as a class. So this is our variable, well, X or here. So it will be so an individual of type person. And then so we define also property weight. So it's a subclass of all data type properties. It's also a functional property. Well, that's kind of some details. Then height in the same manner. So we just do the definition. So if we would create ontology manually, so just describing subject, predicate, object. So but then also creating a hierarchy of types on top of it. So to refer, and then so these are the parts for the individual. So our individual will have weight and a given weight, and height, same for height, and then condition. So we want to get all the records of type person with given height and given weight. So that's it. So that was that is the query we want to supply. So let me see. No, that's not. We want to have it in RDFXML. Mm-hmm. And come on. What is going on? Yes, of course. Again, so after last class finished, so I mean, I just had a more detailed look. So here is the thing. So you need to understand that it's a very large database or knowledge base. I mean, DBpedia, and our query is very generic in a way that we want to get all instances of class person. So it can be like very many. So and there is obvious restriction on the number of people you can number of entries you can retrieve. So here you can, I mean, part of the SPARQL, there is this keyword limit where you can specify the number of entries you want to retrieve. So let me limit it to some small numbers, so just for a quicker demonstration. So let's see. If it won't work by some reason, I have a backup downloaded version. Today is very slow somehow. Come on. Yes. Okay. So yes. Good. So let me go to my download folder. So here is the thing. So let me just open it. Open with. I want some text editor. Would it open in note? No, it won't open in notes. Text edit. So let's see. So that's what it's retrieved in textual forms. So this are our prefixes. No, so it's yeah. These are the individuals that we fetched, right? With some values for the weight and height. So and the weight here, I think it's in grams, if I'm not mistaken. So it's okay, but what shall we do with it? Let's let's do the following. So first of all, maybe we can convert it to all. I mean, to put an extension. All. Yes.
What does EBO mean? If you go to Chromium.
I can even without going into that one. So this is what we define. So DBO is a prefix for the ontology.
Okay.
So that is how we define it. So we just named it such. And here is the full. So it will be substituted by this string. Yeah. So let me just give it some meaningful name. Maybe height, weight, height, weight, O. Yeah, it can work with RDF, no worries. But I mean, and it is actually just a RDF format. And then we go. Well, we can click on it immediately. Okay. Yes. So we have 50 individuals as exactly as we wanted to have. And so if we just examine it, so we have class person, and so it's extremely simple cut of it of an ontology. We just don't have any complex classes. We just extracted assertions, individuals, with some given weight. So here we have all these individuals, 50 people. Now, what we want to kind of work with this ontology, and for this we want to create rules. So let me just go back to this slide over here. So we want to create, say, other meaningful categories. For example, so we can define kind of slim person. So if, for example, a weight is less than or equal to 85 kilograms. So let's do that then. And actually here it's I mean, if you will look at this slide, so it's not a correct syntax. So it's supposed to be, I will upload this new version after. Supposed to be the sign over here. And the same. Here. And also here. So I will trace only creation of one new category, but then here in this example, so we create two, and then we even combine two new categories into a third one. So we start with this, and then I will let you go to back. So if we go active ontology, so I just configure by default there is no this pane in Protege. Let me just remove this stuff. So you need to enable it. So normally you do it in window or tools. No, view. I think it should be in Windows. So yeah, it's over here. So you can play around with it. So this will be a tab. So it will add a new tab, but then you can also have a view. So somewhere here you can select an option to display these rules in the active ontology view. So we want to add a rule. And by the way, so we want to implement, we want to enable a reasoner. And again, so there are different reasoners suitable for different logics that you use. So for all, we use Pellet. In fact, I'm not really sure about this. These two, I can only guess that. Well, this is for existential logic language, working with medical ontologies. But Pellet reasoner is the one we use with OL. And so in the second half of the class, we will talk about what is behind this. So what does it mean? What kind of algorithm runs by the reasoner? So we can start reasoner. So see that it doesn't complain. So if ontology is inconsistent, so you start to see immediately the some warnings or error messages. But here, so we start with constructing a rule. So what one of you know what, I will do it here. Window use new. So here is the name of the rule. You can insert a command. So what does this rule do? So and then here you write the rule, and then if something is wrong, then it's immediately tells you what is wrong. So next. So again, so we check here. And it should start complaining, I guess. Oh no, sorry. Okay, less than or equal. Equal. And it was 85,000. So it doesn't like something. So let me see. So and is here, still doesn't like. So and if you
Gonna see like 20 more wide or something.
no, it's not. Yeah, I will double check it. Here we need to SVRL. So we need to put this prefix where to get the definition of the function. So so if we do like, oops. So expecting, yes, that's correct. Yeah, why? So it liked it. Then slim person, and will be X here. Yes. Still it doesn't like, and of course it doesn't like it because we haven't defined this class. So all the concepts here, they're all concepts, so they need to be defined in the ontology. And to do that, so let me just Control X, remove it. So I will start creating it from scratch. I go into entities, and I need to create a subclass of person. So I add subclass. Slim person. Do you want to make it? Okay, recommended. Then it's recommended. So now we have a subclass, sleeping person, and it is empty at this moment, of course. I mean, we haven't populated it with anything. But again, so now we go to the rules, and I will copy it. So now, it doesn't complain. So now this is a valid all concept or term, and then it will populate the individuals of this term. So, okay. And so let me see. So what's going on? Did it populate anything? No. Yeah, that's what I want to do. Reasoner, synchronize reasoner. Oops. Yes. So now, if we go here, yes. So here, we have populated it with new entries. Yeah. So this is this simple demonstration showed how to create a new class that wasn't part of the original ontology and do this manual reasoning. So we found that it's useful subset of people that is subsumed by class person. So that have this characteristic. Yes.
In the second lab, we do like similar things.
This part with the swirl is an option is optional.
Yeah,
but it's pretty much
like a different way of doing what we're doing in the lab.
It is only different in a way that I mean, here we just took the initial topology, the ontology from somewhere. I mean, but otherwise it's pretty much same as in lab 2. So let's take leg stretching break and have a look at what was behind the reasoner.
Han hade gått med balletten så att han ramlat av i säcken. Och så fick han alla de här grejer precis här. De var så fruktansvärt.
Men visst är det snabbt så här. Hörde det inte ibland som att det rördes
Shall I continue? Maybe if you're not sure. So what we will do now, we will have a kind of a flashback to the first half of the course, and maybe you can relate what I will be talking about somewhat to what you did in Lab 1. So we will talk about again. So what OL, I mean, as a language, is from the logic perspective. So in the first module of this course, what did we do? A tricky question. I know you don't like my question.
We talked about
First order logic, so classical logics, and then in Lab 1, so you did kind of really the algorithmic support to implement so you implemented the reasoner, so you populated the database, the knowledge base with some rules, and then you really implemented the reasoner for the purpose of navigating the agent. So here we have, and then in propositional logic, well, propositional logic is both the language, so it contains the language defined through syntax of constructing sentences, and the semantics, so the how to interpret these different operators. So here in the second part, so maybe that was could be perceived as a kind of disjoint tradition. So we started with some XML stuff. So XML, and then description of some subject predicate object triples, and then some classes and such. So now we will go maybe backwards. So we will talk about the logic behind OL, and to this we need to refer to the terminology we studied in the first module. OL implements a kind of a subset of classical logic. So it can be so all statements can be interpreted using first order logic, and it also extends the propositional logic. So it's kind of somewhere in between. And what is important, so OL, so it's ontology language, ontology web ontology language, is a language for a type of logic which is called description logic. That's what we will have a glimpse of very, very soon. And as I said, so all statements can be written as first order logic predicates or sentences, or obviously it can be interpreted directly. But what I want now is again, so this part won't be tested as such. So the reason for presenting is again to make a bridge to this formal logic that we studied in the beginning of the class. So the description OL is a language for description logic, and description logic is part of is a subfield of logic with many variants, and we will now learn some basic ones. And the idea, so what I want to I want to make a message with this description logic is somehow drill a hole to the reasoner, so to the algorithm behind the reasoner, so the ones that you actually manually created in lab 1. But I mean, here it's a different stuff. And again, so remember this first slide about ontologies. So this description logic apparently has all the properties for describing complex domains of knowledge and assist in kind of rapid engineering. So that's why this is also one of the reasons for kind of talking about OL as a language. So very quickly again, so we learned about syntax and semantics of propositional logic and first order logic. So some slides will I will just switch very quickly through. So in description logic, so sentences are either true or false. And then so we have concepts and relations between concepts, which are called roles. And then we have also individuals, of concepts. So again, linking to the definition of ontologies. So we have these T boxes. So we can identify in a knowledge base parts corresponding to definition of concepts, like mother with daughter is mother, and of all things. So now we will also talk about some semantics differences. All things who are parent of not females. Mother, what is that? All things. Why did I mess up something with this sentence? Let me skip this. I somehow flush my brain on that one. Maybe I will come back to it. And then we have the assertions, so basically the individuals that belongs to a certain class. And then so description logic can come in different flavors depending on the complexity of situations that it can describe. And so all these different flavors of description logic, they are encoded with letter combinations, which I listed here. So the basic one is attribute language. So it's this is a language that allows this function, description of this concepts and relations. Then well, frame language, existential language. Just again to know that there are different flavors. So basically each modification incorporates more complexity or more expressiveness that allows to describe complex concepts. And then you can so a specific incarnation or implementation of description logic may, for example, include complex concept negation. And in this case, so for example, an attribute language with complex concept negation would be called ALC logic. Or if you, for example, so if you create a language which is attributive language with concept negation and transitive rules, then this type of logic in short will be encoded as S. And then basically again, you can create a language that include one or another or several of these different hierarchies, and depending on them, so you will have different acronyms. So, and I mean, I just presented these 2 slides for you to, as a reference to decode these names over here. So that's what kind of logic supports by OL language. So OL language, OL is a language that we use to describe the ontologies, and then apparently, so now we can decode that it supports that it is an attributive language with transitive rules, are limited complex role inclusion axioms, reflexivity, irreflexivity, etc. O nominals, I inverse properties, Q qualified cardinality restrictions, and then we will use data type properties like values or data types. So all this, so now again, so, if you just look at what kind of information you have in your pizza ontology, for example, so you can immediately kind of link to the type of description logic that can be that OL supports. Yeah, and I have already shown that these examples of SNOMED ontology or Go ontology for genes, and these ontologies, so they implement this kind of description logic. But again, so for us, so we resort to the simplest one, so which basically allows to atomic negation, concept intersection, universal restrictions. And I want to use this ALC logic to give you a feeling of what kind of algorithms are running to enable reasoning. So running behind reasoners. So as previously, so we have T boxes, A boxes, concepts, roles, which represent binary relationship between individuals, and complex concepts. So we can construct using different logical operators. So, and here are the examples. The language, again, so you can probably, so what we are doing now, we are formalizing. So we are, as I said, we're going back from this XML kind of description, which is a language, into more formal logic language, on which we can do reasoning using logic formula. So we have this constructors, we have existentials, and so they're kind of interpreted slightly different. I mean, there is a kind of different semantic touch on it, and different concepts how you construct. So for example, a formula with an existential, like for all, so this is also a concept, or there exists, it's also a concept, etc. well, these intersections or unions, so this is self-explanatory. So maybe so here we can spend one or half a minute and read the interpretation for of the for all symbol and existential here. So especially look at the example. So if we have for all parent or female, so it's all. So we have the things, and those things are parents, and so they parents of and their children are female. It's not that it's like for all, like in the previous case. It's so it's a concept. Defined in this way or interpreted in this way. The same goes for this existential. So if we have this, there exists a parent of female, so it's interpreted as things with a female child. And things means that it can be, well, either male or female. Yes. So we have axioms that they come in two forms: subsumption or equivalence, and assertion. So basically, the individuals. So now we create a formal description for them. So it's A is an individual of concept C. R is a relation between individuals A and B. So R is a role or relation. And then we have, so that what any all ontology is. So we have, we can define or we can find a part of the ontology describing the concepts, so T-box statements, and then we have individuals, A-box statements. And now, so okay, so we can turn this XML description into more kind of logically digestible form, which will where axioms will look like this. So so we have animal and biped, so they are a subclass of person, or woman is a person and female, etc., etc. So we basically can do this kind of transition. And then, so for the individuals, we have this kind of statements. So coming back to reasoning, so that's what reasoners do. So I will not repeat myself. So consistency checking, concept satisfiability, instance checking, so etc. So now we will talk about, again, so very we will consider a high level functionality behind the reasoners. So if you have now this ontology in this form, or rather in this form, so which you describe it all or whatever language. So what actually is, and then you can obviously interpret it in this more formal way, so which is kind of used for logical reasoning. So what happens now? So what can you do to implement this kind of reasoning? So most or all description logic reasoners, they extend a method which is known as Tableau algorithm, if you have heard about it. So essentially, we want to break down a given formula, so representing piece of knowledge, like combination of concepts and such. So you want to break it down and represent it as a graph. So I mean, and we are talking now about really an algorithm for automatic execution of this functionality. And and this is the main assumption, so that the database, the knowledge base, it consists of such axioms that are unfoldable. So it is possible to take any formula and then basically unroll it into cycle-free structure. Well, there are some also formal definitions which probably are not critical at this moment for next example. So the general method is pretty much similar to what we used in propositional logic. So we will check satisfiability of a certain concept. So whether, well, we will check whether our knowledge base entails certain concept, and to this we show that we will demonstrate it by contradiction, basically. So we will prove unsatisfiability. And as I said, so Tableau is a graph representing this model. So we start with these modifications again. So this you met similar formulas you met previously. So you substitute the subsumption notation into an intersection. Yes. And then what you do, you negate and unfold. So you perform these two operations. I will give you now an example so you don't, so that it will become clear. So essentially, so here are the rules that are applied to this logical equation that you give to a reasoner. So that you also can recognize from previous exercises. So these are nothing really special. And the algorithm itself is that given a certain definition of or logical sentence, to build a tree that represent this sentence. And in this tree, we will have so the edge will correspond to a relation between different individuals. So to prove satisfiability of certain concept, again, so we supply a concept which is written in maybe complex or represented by a complex logical expression. You start expanding it to turn into this negation or negation normal form, and check whether you have so-called clashes. Clashes means that in the same set of, so in the description of a node in this graph, you have this contradictory labels, so that, for example, both positive and negative or negated concepts are present. So if a concept can be expanded, so without any problems, so without clashes, then it is declared as unsatisfiable. So, and for the expansion, so again, so if, given a concept, so you want to unroll it, so you have this 4 rules. And let's check what it is. Let me see if I am. How to best represent. Yeah, maybe I can. Yeah, let's do it on the example. So there is this step when you convert a logical expression into a graphical form. So basically, a node in this graph, so a node of a tree, corresponds to the enumerated concepts which appear in the end, or in the intersection equation. So let us let's see. So we have this knowledge base defining a vegan and vegetarian. So vegan is a person that I mean, of all people that eats eat plants. And the vegetarian is, well, it's an extended thing that says that it also it's dairy. So we want to check whether vegetarian is well, vegetarians are subsumed by vegans, and to this we need to show that this equation is true, or to show that it is unsatisfiable. So maybe now I want to do some drawing on directly online. Oops. So we are about representing this equation now, person and eat plants and then the negated part graphically. So we want to unroll it. So what do we have here? So we have 2 intersection operators. So we have 3 concepts that that we intersect, and that means that I mean, so the first expansion rule. So so if we have this case, then we take each of the concepts in this relationship and form a node with the labels including all these concepts, meaning that so let me see. So if we have, say, so we want to create a tree. So I will draw two descendants, but it will be actually only one. I just want to show that we want at the end we want to create a tree-like structure like this. So that's what the algorithm does. So, and this structure should correspond to this equation at the end. So what we do here, so when we encounter a concept in this form with intersections, so we take each of the concepts in the intersection and say and create the first node in the tree. So we we say that okay, so we have and we label. So the our label will contain person, and then this thing over here. And this whole thing over here. So this is about this creation of this first node. And now we start to analyze this, obviously, I mean, this set of label, or this label contains complex equations that need to be unrolled further. So we start to modify this complex formula, and using other expansion rules. So let me mark it as by different color. So that we created this node. Yes. So this node we created just analyzing, dissecting the first equation into the parts included, into the concepts included in the intersection. So it corresponds to this step. So now we analyze this complex label, and then we try to modify this complex equation until we actually boil down to atomic concepts. So the expansion for this union rule, so here, is that well, you can add either of the labels or you can add either of the concepts to the label of the node. So we try one by one. So what happens if we add first concept from the union to the set of labels? So we exclude this one and add only the first one, which is negation of a person. And this is the case where within the label of a node, we have both concept and its negation, which by definition is a clash. If this is the case, if we just encounter these two concepts, one which negates the other, so the algorithm goes back. So now, okay, so it analyzed this thing, and now it tries to work with the second concept in the union. So so to do that, so let me just copy this thing. To do this, so it basically start to work with this existential. So existential means that so out of so we need to split the current node. So it means that there is another node that belongs to this concept with this property that eats plants and dairy. And that what is happening. So a new node is created, so this one, and a label for this node, a label for this node is the equation of the eats, and the relationship is the label of the edge, so between these two concepts. So that is how it works. So how you interpret is that so there is an individual that doesn't eat plants nor dairy, and belongs to and in relation to the previous concept via the well with the label eats. And as soon as you do it, so the only thing left is this all thing. So so the expansion rule for all is that it needs to be propagated along all the children. So it is. It means that so having this equation in the first label means that so it's definitely part of the of this class. But then you also add plant into the relation eats into the new node, and this becomes this comes into clash with this with the node plant concept in the new node. So basically, in this very simple example, so the algorithm broke down the initial model of this form into the cases where it cannot be further expanded because it reached the atomic sentences, and in both cases, so while unrolling, so it encountered clash situation, and so that means that basically we shown that the subsistence property holds. So all in all, so whenever we run reasoning, so it kind of it has internal representation of your knowledge base into into this digestible form, so logical form. So it performs this well, one or another implementation. It has one or another implementation of the Tableau algorithm, which breaks down these equations into graphical, well, into the graph form, and checks and proves by contradiction in different properties. So that's what is going on, more or less. Yes, and that is what I wanted to show you today. So we talked about all, but from a logical perspective. And again, so that indeed, so it's not just well, a language that is well specific for annotating web resources, but rather it implements particular class of logic which has practical importance in different domains. And that is it. So good luck with lab 2 and such.